Excellent. Thank you. So I am honored to be able to introduce Dr. Byran Henson today. Byran got his PhD in chemistry from UCLA and came to Los Alamos in 1991 as a climate change distinguished postdoctoral fellow. He did work on atmospheric chemistry and published on the climate of Titan and developed models that were incorporated into stratospheric chemistry simulations. And then being a history buff as well as a scientist, Byran can actually remember where he was when he heard in 1992 about the moratorium on nuclear explosives testing. This is a challenge to everyone. Think if you can remember where you were at that moment. I certainly can't. But that was formative in Byran's career, and he began studying secondary high explosives at Los Alamos and applying his background as a physical chemist and his immense scholarship to understanding the behavior of the class of explosives, secondary high explosives. And I have had the privilege of working with him on this problem for the last couple of decades, and so I am happy to introduce Dr. Byran Henson to tell us about what he has learned on the chemical kinetics of secondary high explosives. So Byran, if you'll go ahead and teach us all.
Thank you very much, Laura. I am Byran Henson. I'm going to speak today about work we've been doing, for the last 20 years on classical chemical kinetic approaches to understanding how secondary molecules come apart and release energy in applications like initiation and detonation. This is, of course, an enormous field and a voluminous literature, and I'm not going to attempt a review with this talk. But I do want to give those of you who have been familiar with us and following us for some time a snapshot of where we're at the moment in putting together these models that actually now go all the way to product formation and allow us to really refine applications of these kinds of ideas. I do want to mention a couple of people, Craig Tarver at Lawrence Livermore National Lab, Tom Brill. I was very fortunate to build work upon their work. You'll see some of that in this talk today, to know them and to talk to them, and I want to express my appreciation for that fortunate fact. And of course, then having said two names, I leave out the rest of you. I can't imagine how this work would have ever proceeded without the context of the APS topical group and the shock compression meeting, which we've been attending for most of the time that we've been working on this. So really, I have a lot of appreciation for all of you that are here listening today. I work with the team at Los Alamos with Laura Smilowitz, that just so graciously introduced me, and Pam Boland, and Natalia Suvarova, and Dennis Remelius. This is our team slide that we use. We break this down into two efforts, basically a largely experimental effort led by Laura Smilowitz and the Lars radiography. I do a lot of the theory. Pam Boland's spinning up some new experimental techniques as well, and then again work with Natalia and Dennis. This slide is really meant to indicate to you that even though at times this talk may begin to seem somewhat esoteric, particularly when we're talking about the mechanisms by which a crystalline solid begins to disorganize and make room for chemistry to happen, that we really have a very pragmatic application in mind. This is data and some illustrations from the Lars laboratory scale radiography technique that Laura Smilowitz has developed. We have radiographs here. We have 30 nanosecond radiographs, 3 nanosecond visible imaging of the surface of an initiating detonator. We are able now to really refine the spatial properties of the ignition, what we believe to be an ignition event followed by initiation, the internal structure of these processes, and to really unravel the mechanisms of function. This can either be a detonator, or it could be the end of an accident scenario where we're worried about the transition to detonation. But at any rate, all of this work has a very pragmatic and a very practical application at the end. And by way of outline, I'll start with just a discussion of thermal response in secondary explosives. As I mentioned, we believe that much of the behavior of these materials is governed by temperature. That's not to say that knowing what that temperature is, or measuring it, or understanding how it will come about is easy. It's just that if you know the temperature, we're beginning to think that we understand the chemical kinetics that will follow. I'll talk about applications of these ideas to secondary explosives, and then indications of the mechanism by which the explosives respond to temperature in terms of crystalline imperfection. A brief assessment of the impact of some of these ideas fairly early on in the talk, and then a discussion as extensive as we have time for about global models, past the really complicated bit of solid decomposition on to more fluid-like classical chemistries of intermediate consumption, and then finally you're left after a very short time with an extremely high pressure, high temperature sample of water, nitrogen, and carbon oxide. At which point, we believe with these mechanisms we can do things like calculate pressure and pressure derivatives, lean on classical techniques from the method of characteristics like wave coalescence, and really begin to talk about having applied temperature, either by accident or intention, to a secondary explosive. Calculate how that explosive comes apart, calculate how it releases energy, and not just know when things are going to happen, but what kind of things they're going to do, not just when we ignite, but what they're going to do. And then I'll have some specific applications of these ideas that I follow within the end. So this graph on the left is how much of this began. This isn't actually the illustration from the Dead Symposium paper back in 2002. We've populated it with some more data, but it is a version of that graph. On the left, we have the ignition time in a number of experiments on HMX, plotted logarithmically from 10 to the minus 9 up to something like 10 to the 5 as a function of the inverse temperature. And the real breakthrough here was the realization that despite actually a lot of opinions to the contrary at the time, and perhaps even still, the complex chemistry of this very complicated molecule coming apart manifests itself, at least through the prism of ignition, in a very simple way, like a classic Arrhenius behavior. And by that I mean a temperature-dependent process governed by an Arrhenius rate constant. The row of equations on the top, the very far left, is a rate constant with a temperature-independent prefactor, and an activation energy. We will express that typically as a characteristic time, the inverse of that rate. The two things are interchangeable, and I'm afraid I probably use them interchangeably more often than I intend to. But if you look at it that way, one can then take the logarithm to replicate this logarithmic plot I've shown and see that you basically have a characteristic time that decreases, and you plot, the inverse temperature from reverse, from high to low to 0, you're basically looking at the characteristic time to ignition decreasing as we increase the temperature, basically to infinite temperature. So you have an intercept, which is the rate at infinite temperature, and an activating energy, which governs that slope. So that was very exciting to realize that in 2002, that it was a single line. More important than that, though, subsequently we determined that it's not an arbitrary line for a given explosive. In other words, for HMX, we could construct that line not simply by fitting it, but by constructing it from two energies that were known from the crystalline thermodynamics of HMX. That this ignition line, this characteristic time, is actually the geometric mean of two rate constants formed from rates of sublimation and vaporization. This is actually quite stunning, and provides, as I'll elaborate in the rest of this talk, a number of clues as to what might possibly be going on in the mechanism of decomposition here. But I want to reiterate that what we did in looking over the broad range of temperature and fitting these ignition data is improve the extrapolation of this rate from the low temperature region where you can measure it to high temperatures where you want to use it, and discover that it's a single line. But we were able to fit it with sufficient accuracy that we could determine that it actually is two specific things. It's an activation energy made of the enthalpy of sublimation and vaporization. And so you have a rate constant that ends up looking like this along the bottom. We have this geometric mean, which is the rate constant for this single line. It has a temperature-independent prefactor, and it has a temperature-dependent activation energy. That activation energy has a form independent of this fit now. It is something we can calculate with thermodynamic properties. We can measure energies of sublimation and vaporization in a number of ways that I'll discuss in just a moment. And we have a complicated temperature-dependent prefactor. Now, this is an Arrhenius rate constant. It is A, e to the minus e on RT. A is a bit more complicated now, because sort of in the tradition of transition state theory, at least its early applications, and rate constant behaviors on free energies, we're going to build that temperature-dependent prefactor out of the entropy, which is known. as well as these prefactors. This is what I will really refer to as the prefactor, these nu sub and nu vap terms. The hope is that in expressing this geometric mean in terms of constants that we know independently, we are using this formula and this behavior to help us narrow in on true mechanism and hints about what's actually happening, independent of simply a more refined fit to the Arrhenius rate constant. And it's important to note here that having measured this ignition line, we've really only fixed with this line two things. This whole term, which we can decompose now into these known terms, and this one prefactor, which if all we have is the one ignition line, this is related to a single measured number. So we may know the entropy of sublimation and vaporization, but we cannot independently determine these two prefactors simply from ignition. We do, however, have another phenomena that we lean upon to understand these things that I'll talk about in a little bit. But for now, HMX is a very particular example of secondary explosive for us because it has been measured so well. So on this slide, I show the phase diagram, a simply rendered phase diagram for HMX, the vapor pressure as a function of temperature, with an inset that includes the ignition data I just showed, and then another set of data measured by Tom Brill and Stefan Thanel and a number of people 10 or 15 years ago in the context of propellant studies is going to provide us an additional equation for constraining this system. The first reason for showing it in this way is that I really want to communicate the fact that when I say that we are building the chemical kinetics of these secondary explosives from their thermodynamic properties, I really mean just exactly that. That we are going to take energies of sublimation and vaporization that you could deduce or determine in combination from a heat of fusion. You could determine parts of this parameterization from the melting point. If you have the vapor pressure as a function of temperature over the crystalline solid, you could determine two of these parameters. So there are various ways, simply applying thermodynamics and analytical physical chemistry, to determine four of the parameters that make up these two rate constants. But we're still left trying to determine the prefactors. Tom Brill published this in a number of papers, but in applying a technique that they developed, temperature T-jump FTIR spectroscopy, they were able to measure the rates of evolution of two families of products from HMX. And if one associates the rate of appearance of those two products with these two rate constants that we're combining as the geometric mean in ignition, one has another equation to try to fix these prefactors. In other words, the slope of this line that Tom Brill published, the ratio of these two product families, which we assume to reflect the ratio of the two rate constants, you have another equation. And if you have another equation, you now have two equations where only these prefactors are unknown, and you can fully constrain the 6-parameter two rate constant system that makes up this one ignition line for the example of HMX. And that's quite powerful. There's also another kind of experiment that we use to inform these phenomena, and it has been labeled melt acceleration. It's a phenomenon that was published on actively in the 60s in basically the Russian Journal of Physical Chemistry. And, you know, when one looks back at the history of these sorts of things, many things are fortunate, and one thing in my case that's fortunate is that Los Alamos happens to have a very well stocked compilation of the Russian Journal of Physical Chemistry in translation going back all the way to the 50s. So a few afternoons in the dusty basement of the library here at Los Alamos revealed a wealth of really interesting and relatively independent and informative data on these secondary explosives. This is what that sort of data looked like directly from the publication itself. It is a rate constant published as a function of the inverse temperature. This is PETN. PETN is another secondary explosive molecule. It exhibits a really wonderful curvature in the melt acceleration that I'm showing here. The melt acceleration phenomena itself is the observation that for a number of secondary explosives, if you measure the rate of decomposition, and it was measured back in the 60s, typically with manometric techniques which looked at product formation above the solid. The rate of decomposition as a function of the inverse temperature was essentially linear away from the melting point, but as you take measurements at different temperatures, independent experiments conducted at different temperatures, at temperatures that are approaching the melting point, you see this acceleration in the rate. It begins to go faster and faster, become nonlinear, and define by its asymptotic behavior the melting point of the material. Wonderful, really interesting set of observations. In the literature of that time, there were a number of explanations of this phenomena having to do with basically liquid components of the sample being formed essentially by freezing point depression because of impurities. And there were impurity concentration formula developed for the acceleration of these rates. We're going to offer a different interpretation of that, having to do with the inherent formation of a liquid layer on the surface of a molecular crystal, explosive or not, as you approach the melting point. But suffice for now to say that we also have a formula for the characteristic time for this phenomena, and we've been publishing this since, I think, 2010 in a DET symposium. The interesting thing in this formulation is that at low temperatures, this linear regime actually expresses a linearity, a slope, that's parallel to the ignition line. And I'll show that in a figure in just a moment that makes it much more apparent. But essentially, in this formula, you again see this geometric mean appear as a function of those two rate constants. We have here the thermodynamics in the form of activities, as I probably didn't point out in the original slide, but the F's are the free energies of vaporization and sublimation in the exponent of the natural log. And this function captures basically the asymptote, and this function defines the equilibrium melting temperature, and so this captures the curvature here, and this captures the linearity at low temperature. And if you pick for HMX, you put together this whole thing on one big diagram, you actually are beginning to map out quite an amazing representation of the behavior, both thermodynamic and in terms of ignition, of a secondary explosive. This is the melt acceleration data for HMX, which HMX I didn't show on the last slide because it doesn't really present data in the regime of curvature, or at least there hasn't been any obtained to date that really pleasingly illustrates this. But in fairly recent experiments, actually since 2000, I believe, just extraordinary, excruciating measurements have been made at very low temperature for HMX, which determine very well this linearity and establish very well the parallel nature of melt acceleration at low temperature and ignition. And we take advantage of that as a really important component of this. And I've plotted here the melt acceleration, the ignition, logarithmically as a function of the inverse temperature again. I've also published, plotted as the red dashed lines the sublimation rate constant. I've plotted it as the characteristic time, and the vaporization rate constant as the characteristic time. Now, what HMX enables, because we have so much data from it, from both of these phenomena, is the observation that at infinite temperature, the intercept, the rate at infinite temperature of the vaporization component of the rate constant and the linear component of melt acceleration are the same. And we assume that not to be accidental or coincidental. We assume that to be a function of mechanism. If it's a function of mechanism, it's an additional equation, and you can do a bit of algebra on the offset between these two linearities, the ignition dependence and the low temperature melt acceleration dependence. And if one does that, you get a prefactor. You get the constant that defines that offset, which is immediately interesting. It's a function of the prefactors, which is unsurprising, but it evokes, simply because of the thermodynamic representation of these independent components that we're combining here, the entropy of fusion. So now melt in melt acceleration is not just the semantic description of something that does something as you approach the melting point. We've now got to handle an evocation of basically the entropy difference in the crystalline and solid environments in these materials as being somehow implicated in the displacement of melt acceleration from ignition. And that's actually extremely satisfying and very interesting. In terms of applications to secondary explosives, you've already grasped, I'm sure, that we're describing much of these kinetics in terms of the thermodynamics of these molecules. So, since we are able to do that, all of these molecules have their own crystalline thermodynamics, and so how applicable are these ideas to the family of these explosives? And it turns out it's going to begin to look very applicable. This is now a PETN phase diagram, just as a reminder of where all of this comes from. Formula that define again the activity as a reminder and melt acceleration. But this is a collection of data, again, much of it from the previous literature on tetrol and PETN, on DATB as opposed to TATB, on HMX. We have put together an experimental technique here at Los Alamos, actually led by Pam Bolin and Natalia Suvarova, where we are using X-ray diffraction rather than manometry to begin to measure these curves as well. And these are data on TATB that we have taken in our lab, and on CL20, and actually on the sugar fructose, lest we think that these mechanisms are simply applied to explosives. We've got a sugar sneaking in here and behaving in the same way. This is a wonderful technique. I think it's going to prove to be very important. Pam's in the middle of getting it published as we speak. I would assert that by this asymptotic behavior, these two measurements of CL20 and THB are probably the best measurements that there will be in the literature of the melting point of these two compounds. Reactivity near the melting point typically confounds our ability to measure it accurately. In this technique and with this phenomena, actually the reactivity is incorporated, and the acceleration of reactivity guides you asymptotically to the true melting point. So it's actually quite fantastic for applications in explosives, and probably also just other really important and difficult applications like understanding the melting point of fructose when caramelization continues to get in your way. The same story holds true for ignition. These are ignition data, similar to the data I initially plotted for HMX, but now for PETN and for THB as well. THB, Livermore did one-dimensional time-to-explosion experiments, actually on all three of these molecules. But with THB, uncompromised by proximity to the melting point and as extremely stable as THB, it gives you a really nice line already, even independent of an assistance with this known slope based on the thermodynamics. PETN is very difficult. But let me back up just a bit and explain what I mean by difficulty. This is an illustration of how exceptional HMX is. HMX gives us a view of data almost throughout the range of extrapolation that we historically have had to deal with, where you can make your measurements typically up here, and you have to extrapolate for applications in initiation and detonation to a regime many, many orders of magnitude away. This is an illustration of what kind of guess that is without data like we make with THB. PETN actually confounds that extrapolation even from the outset, because PETN ignition, even at low temperature, is convolved with melting. It's convolved with melt acceleration. So making an extrapolation like this with PETN would be difficult anyway. So this plot is both an example of how these ideas are applicable not just to HMX, but to other explosives like PETN and THB from the point of view of ignition as well. It also is reflective of the main historical problem in this entire endeavor, the fact that most of your data is populated in the top left-hand part of this graph, and what you really want to do is extrapolate it down to the bottom right-hand part of this graph, and that extrapolation has been perilous from the outset. But to concentrate for now on this thermodynamic foundation for these mechanisms, I'm going to normalize these two sets of data that we just saw and see if, as all physical chemists always want to do, we can put a bunch of different data from a bunch of different laboratories on a bunch of different molecules all on the same plot. Now one could do that fairly simply by simply taking the prefactors out of this formula for ignition, for instance, multiplying it on this side by the time, and you would have a unitless representation. But we can do something more interesting than that. We can actually manipulate these activities. If we divide through these formula by the activity of vaporization, we generate ratios like this. And this is actually another formal activity. The activity of sublimation divided by the activity of vaporization leads us to actually a liquid activity. And I'll mention in a few slides from now, we've published a bit on this. This is formally the ideal liquid activity of the liquid phase of a molecular crystal in the presence of the solid at temperatures below the melting point. I'm not going to belabor that point too much just yet. I'll talk about it again in a couple of slides. But this exercise of rendering these formula dimensionless is not just getting rid of units. It is also going to help us inform mechanism. So if one basically divides out these activities as I've just described by these two formula, you end up with these dimensionless representations that are now reduced times to either ignition or melt acceleration as a function of the liquid activity. And when one does that, of course, you get some really interesting stuff. These are the three ignition plots as I've just shown. If you take the times to ignition, multiply them by the vaporization rate constant at that temperature and that function of the entropy of fusion, and take that as the dimensionless ordinate here, or abscissa, I forget which, and then take the temperature at which that point was measured and make the ratio of the activities to plot as a function of the liquid activity, one gets this nice linear representation over many orders of magnitude for all the ignition data from a number of different molecules. So we are really beginning to narrow in on something not just explanatory for the rate of decomposition of HMX, which is where we started 20 years ago. We're really beginning to elaborate and describe a mechanistic representation of something that probably at the end of the day will be a fundamental molecular definition of why secondary explosives are what we have heuristically known them to be for some 50 years. The same thing can be done for melt acceleration. If you take all of these data in the characteristic time and the inverse temperature and you affect this dimensionless reduction, you end up with actually, I think, a rather more pleasing, curved and asymptotic, but universal representation that captures all of these molecules. So one last bit about mechanism that we can deduce from this. As I mentioned, this ratio that we're using to render these representations dimensionless is an activity. It is a liquid activity. It is essentially the vapor pressure observed over the solid relative to the vapor pressure of the phase itself, the liquid. That is the definition of the activity. It's actually proportional in ideal solution theory to a mole fraction. If this were a binary solution, one component's vapor pressure would be lowered over the vapor pressure of the pure component by just its mole fraction in solution. That's going to turn out to be a startlingly accurate analogy to what's going on here. And this is just a concession that for molecular crystals of high vapor pressure, the interface between the solid and the vapor at ordinary temperatures is not a refractory interface. There is a layer of disorder. It is a layer that can be measured. It's a layer that's been measured and discussed in the literature for something like 50 years. We've published on it something like 15 years ago. We developed a formula for the temperature dependence of this thickness, the number of n in the column divided by m in the lattice, that is a function of this liquid activity. And of course, if you do a bit of algebra, say solve for A as a function of n and m, it turns out that this liquid activity is a mole fraction of this surface, this refractory lattice layer of disorder system, as though it were a binary solution. This by itself is really interesting. It turns out this additional formula that we needed to make melt acceleration drive asymptotically to the melting temperature, it turns out you can solve that for m and n too, and it is even a more interesting representation of a mole fraction. This is now the mole fraction of the solid lattice points in this binary solution, in a solution where the disordered units, the disordered elements have to be taken two at a time. This is a paired statistic. This is the kind of thing that arises very naturally and all the time in applications like dissociation, where you have one thing that, say, absorbs on a surface, dissociates and occupies that surface as two things, or one thing that dissolves as an acid in solution and then participates in the colligative properties of that solution as two things. This is implicating second-order kinetics. Somehow with this interfacial enumeration of the statistics of disorder, and it's doing it all on its own. We did not set out intending to do this. We set out intending to have a curvature in our melt acceleration formula that the data indicated, and in doing that, we are confronted with the reality of these statistics. And in fact, this formula for the reduced dimension in the melt acceleration forces us to confront a number of realities about the mechanism, all of which we've already discussed, but that I wanted to kind of summarize here, where we've got the entropy of fusion evoked to explain the displacement of low-temperature melt acceleration and ignition. We've got the liquid activity as governing the reduction of temperature in this representation, and it actually appears as the square root, which is another indication of second-order kinetics. We have this more complicated function of the liquid activity, which when you reduce it, turns out to be a paired second-order statistic and also indicates second-order kinetics. And just the fact that the whole thing hangs together as a function of the liquid activity is quite astonishing. And I can't really stress enough, I think, although we're still exploring this ourselves, how many things have to go right in this representation for all of these data to be normalized in such a way, to lie on top of each other on these reduced curves in such a way. There's no arbitrary scaling here. There's no fitting here, except to the extent that we needed ignition and acceleration data to fit those prefactors. They were fit independently, and then when we affect this reduction to the liquid activity, they all quite happily lie on top of one another, and that's quite astonishing. So this is all, if you're a physical chemist, just good, clean fun. But is it informing us in this, what I claimed would be very pragmatic and applicable exercise in understanding classical chemical kinetics? And so we'll take a quick assessment of that at this point. In the left graph here is the same sort of logarithmic plot of inverse rate constant or measured time as a function of the inverse temperature. The black dots are extracted from the historical literature. The criterion we used for those points were that they were ignition experiments, and that they were ignition experiments that were not pre-pressurized, that they were confined, and that they had a very well measured boundary temperature. That specification selected this set of data from the historical literature and enabled us to make that ignition observation. This is a book by Manelis et al. It's around 2000. Also has a really nice, I mentioned that this would not be a review of this field when I started, but this book is a very good review of secondary explosives. And in it, they have a compilation of HMX measurements that go back into the 80s. HMX decomposition measured by any number of techniques, manometry, gravimetric, calorimetric, spectroscopic. At any rate, they lead to these data I've plotted as gray, where the gray line is the publication of a rate constant, and the length of the line is the temperature range over which that rate constant was measured in those experiments. And so one can see that you know, in this idea of extrapolating rate from the measurements at low temperatures is an extraordinarily difficult exercise, because one can pick a temperature, call it, I don't know, 200 C. You don't have a rate constant, even in the historical literature. You've got a range of them that span something like 2 decades. I am the last one, having started out as an experimentalist, to say that all of these measurements except one are wrong and one of them is right. That is not the case. They were all measurements made and under conditions that they knew needed to be controlled, under conditions that the technology of their day allowed them to control, but they were also measurements that were made where we were not able to control things or did not realize that we should control things, and that did lead to systematic differences, the variability in what people were measuring. And what we have noticed is that if you take data basically that pertain to HMX in the delta phase, and you expand it onto this plot, and then you introduce our melt acceleration and ignition curves taken straight off of the slides I presented previously, we see that much of that variability is bounded by these two ideas. Melt acceleration being a curve representing experiments that are truly isothermal. Temperatures are not allowed to run away in those experiments. They are held at constant temperature, and rate is measured at those different temperatures. Ignition is a different prism on this problem. In ignition experiments, temperature is allowed to run away by design. So it is a reflection not just of the rate of decomposition, but also the rate of decomposition coupled to the rate of thermal acceleration. And what we see when we look at the historical literature is that much of that variability is bounded by these two. And so the implications for this variability and these bounds are going to be important as we tease apart this mechanism. At this point, all I really have to show you is this fact. We are still working on the interpretation of what this means, but it's quite exciting, and it renders sensible another exercise, which is if one is writing a simulation and you want to use a thermal rate constant for the decomposition of a secondary explosive, one of the first places you'll go to is Gibbs and Pappalardo. That book is getting a bit dated now, and again, I don't mean to be critical of the book and its compilation. It was the best that could be done in its time. But now we can see that there were things acting to confound the exercise of deducing a rate constant at that time. For PETN, for instance, this is the Gibbs and Pappalardo rate. And you can see how they tried to fit that to a number of different experiments, probably which reflected a number of different environments, which they did not know how to separate at that time. But we can now view through the prism of these ideas and these mechanisms, understand how to separate them into melt acceleration, into ignition, and how to understand the extrapolation should be made based on these thermodynamic parameters which assist in guiding this extrapolation. And we come up with a very different rate constant. And we already know from a number of applications of this work that we're coming up with rate constants that are more applicable and are serving us better in simulations. And we have that for HMX and for PETN and for TATB. So to go on, and probably have to speak a bit quickly, our contribution to this point has been the bulk of this talk, the deduction of these ideas about crystalline mechanism as they stand right now, the formation of the creation of formula for the kinetic representation of decomposition, really are unique to the work that we've been doing here at Los Alamos. I'm gonna begin to talk about more global models, and we're going to begin to lean heavier and heavier on work by the entire community. We have up till now, in leaning on the historical compilations of ignition and melt acceleration. But from here on out, we're really going to be looking at a lot of work that's gone on the general decomposition of secondary explosives. Particularly, we're going to go to the combustion literature for much of the meat of the rest of this modeling. We're going to start out when we try to put together a globalized model of the kinetics with this geometric mean for the overall rate constant. We're also going to need to acknowledge and have the model reproduce the fact that the two channels of decomposition follow independent rates independently. They are not coupled as the mean. So that needs to be a feature of the mechanism as well. There are well-known aspects of this part of the decomposition from propellant research that goes back 20 or 30 years, where people have identified dark zone chemistries that have to do with channels of decomposition where carbon becomes basically unassociated with nitrogen, and we have two different families of intermediates carrying those two atoms. We have a bright zone chemistry that, again, has been labeled by others in the literature. That's not our label. But that channel of decomposition carries the carbon and nitrogen still bound. Those are going to go on to react in order to get us the final products. Also, we're looking for an intermediate complexity of mechanism. We want something like a dozen reactions. Very sophisticated, very complex models exist in the literature for the decomposition of these molecules that were created basically in response to questions having to do with propellant and combustion applications that I want to acknowledge. They are very large models, very extensive mechanisms. Ours is sort of a globalized intermediate between something that you would realize in that literature and something that you might look up from, say, Craig Tarver's work back in the 90s and 2000s. And toward that end, much of our chemistry is going to move from HMX or PETN or another secondary to final products by moving through these intermediates, formaldehyde, NO2, and HCN, and we are going to stoichiometrically aid the permutation of these into final products, basically with hydrogen atom chemistry. And we'll pull some sleight of hand approximations like this, where this reaction will appear in the mechanism, but it's actually a composite reaction that hides the OH dependence and allows us to basically cut the mechanism in half. So for the first part of the intermediate mechanism, we're going to, of the full mechanism, I'm sorry, we're going to take three representative molecules and we're going to begin to take them apart. HMX has been observed to come apart and produce something like these two families, although we have modified these stoichiometries a bit, but something like these two families of products. TATB and PETN, the evidence for this is much more sparse, but we are still going to assume them to come apart along these two different channels, both of which are governed still by these vaporization and sublimation-free energies. These are illustrations of the molecule. These stoichiometries are correct. We are governed by the stoichiometry of the system all the way to final products, which constrains us considerably in how we consume and release energy as we proceed from the parent molecule to the final products. The two channels are fairly pleasing from a physical chemistry point of view. One of them is what I call a rather expansive channel. NO2 leaving these molecules takes some space. It has a very large, what we would call volume of activation, so a very sensitive pressure dependence. The other channel, which tends to quickly lead to final products, is a more condensation kind of chemistry, where the molecule basically collapses in upon itself to form these unassociated carbon-nitrogen families of intermediates. And we are going to make stoichiometries out of these three representative molecules and then make a model out of the subsequent reactivity of those intermediate species. And this is not meant to be taken home by anyone, but for HMX and TATB and PETN is an example of the rate constants that we are taking from the literature to represent things like HCN isomerization, the reaction of HNCO with nitrogen dioxide, a lot of the intermediate chemistry that's going to go on between the parent HMX, TATB, or PETN and the final fluid of water, nitrogen, and carbon oxides is mediated by a network of real chemical reactions with fixed stoichiometries. So it is not a random free energy mixing. It is a network of reactions that take us from here to there. They all have their own temperature dependence. In particular, when HCN is present, the temperature dependence of that isomerization reaction is really important for our modeling, and actually also for the observation, frankly, of the fact that HMX deflagrates like a propellant. Each molecule requires more or less of these families of intermediate chemistries. We are putting together global mechanisms that tend to look very much alike in that we are drawing from similar families of intermediates. The stoichiometries that we use to represent the real reactions are, of course, different, but the framework on which we're building these models is actually very similar from molecule to molecule. This is one representation, or at least a sketch, of the representation as a chemist would like to look at it for HMX. We have phase transition kinetics that can be incorporated if you need. We have what we're calling a lattice dynamics system that I'll mention a bit more in just a second. It's a system of two differential equations in arbitrary progress variables of the solid state chemistry that allow us to take these two independent rate constants and in a natural way have them couple as the geometric mean as we observe in our ignition data. Again, they break down as two channels where these are actually independent, not coupled. Then we have the series of intermediate reactions that take us to final products. This map then becomes basically a series of something like a dozen differential equations in each of those species. These actually turn out to be very important and are probably the most unique of our contributions to this area, which is what I was trying to express when I talked about the earlier part of this talk being most reflective of our contribution. Trying to put together and understand these progress variables, which I think in the end are going to be implicated in crystalline disorder, as we discussed with that liquid activity and liquid imperfection. And they are going to help us to understand how to take this molecule apart and begin to produce these intermediates. This is really important because at the end of the day, well, actually in a couple more slides, we're going to talk about calculating pressures as intermediates are formed by these processes. And we're going to take derivatives in time of the pressure as decomposition proceeds. And those derivatives are going to determine things like wave coalescence distance and how a given environment leads to ignition and how that ignition leads to shock physics. So the form of the equations that result from this modeling of the solid decomposition actually turn out to be quite important. Then we follow with a bunch of differential equations that are just taken from classical chemical kinetics and measurements of others in the combustion literature. We hang an energy equation on top of that, and we have a set of differential equations in each of these molecules. And when you integrate them, they begin to look like this. So we have three of these sets of differential equations. We have one for PETN, HMX, and TATB. Actually, we have others, but these were the first three and the ones that we're publishing on at the moment. If you integrate this system of equations at the same temperature, we'll pick 1800 degrees Kelvin. That's something like a detonation temperature. And we just do an adiabatic integration of those ordinary differential equations as a function of time. And you get the classical result. You could read this out of the kinetics section of your physical chemistry textbook, not these particular ones, but ones that look very much like it, where your parent species, the solid product, goes away in time, where intermediate species appear and then are consumed and go away, and in the end, final product species appear. One can use the energies consumed and released as a function of the stoichiometry of each of these steps, and one can generate a temperature, which I think is gray in these plots. And you can take an equation of state, and then we do the very simplest thing. We take a JWL equation of state, and we put all of the fluid molecules that are produced in one bag and call them a single species, and we deduce a pressure as a function of time during this decomposition. And already, something's happening that we were hoping for, and one should hope for in putting together a mechanism like this from molecules that we already know so well. The molecules are beginning to express themselves here. 1800 degrees Kelvin is something like a detonation temperature, and we can see that PETN is completing its decomposition, igniting, and ready to serve a shock wave in detonation after about a nanosecond. HMX after something like tens of nanoseconds. TATB something approaching a microsecond. And this is already beginning to sound qualitatively, actually somewhat quantitatively, like reaction zone times in the detonation of these three molecules that we already understand so well. Now, we're not fitting these calculations to accomplish that. We're putting these equations together in a very constrained way. Essentially, the only things that are not constrained in this calculation are those two independent prefactors that we had to fit from the ignition data so many slides ago. And we have some degrees of freedom in putting together the stoichiometry, but at the end of the day, the atoms all have to add up at the end, so that's only a limited degree of freedom. These are actually extraordinarily constrained calculations that are already reproducing things that we know about these molecules. In order to make the jump to shock physics, we want to integrate, say, for instance, I think this is PETN, and I think the boundary condition is probably a boundary condition offered by measurements of temperature in one of Laura's exploding bridge wire experiments. If it's not, it will be in a moment, although I'm beginning to run out of time. You can integrate as a function of a thermal boundary condition these kinetics, and actually this is HMX, it's not PTN, I'm sorry. One generates pressure as a function of time. You can take the derivative of that pressure as a function of time, and actually already it's getting interesting. That derivative is important in coupling to shock physics, and that's why we're showing it in this slide. But it's not just one peak, it's two. So we're delivering the derivative pressurization from an ignition to the surrounding medium in two impulses, which is beginning to get really interesting. And you can see that again here. We actually try to make a simple assessment of the shock physics from a given integration without actually having to put this into a complex hydrocode, because that involves a lot of effort and the consumption of many resources. And one can actually do just a simple sketch of what's happening if you use a wave diagram as we have here and the method of characteristics. So what I've done is, as a function of time, the same time here over which we're integrating the decomposition, one begins to emanate characteristics. The characteristic velocity emanating from an ignition location is the particle velocity plus the speed of sound. And for those not intimately familiar with the method of characteristics, I apologize. You'll just have to take it for granted from me that one can emanate these rays of velocity from points as a function of pressure as the pressure proceeds through the decomposition. And we see that early on, we're emanating fairly low velocity characteristics. As the pressure increases and as the origin of each emanating ray condenses according to the derivative, one sees that these characteristics steepen. And they end up intersecting and coalescing as a function of time and at a particular distance. And that is the phenomenon of wave coalescence. And that is a fairly simple explanation from probably the last person in the room that should be offering such an explanation of what a hydrocode does much more rigorously by integrating the system of Euler's partial differential equations. But what we can sketch out here qualitatively, and for instance, under the conditions of this, under these conditions and at this temperature, we generate an ignition that one would expect to lead to shock physics and maximize the steepening of the emanating pressures after, very, very quickly, within nanoseconds of the ignition, and over a dimension of something like millimeters. And we can use that then, and I'll skip this slide because we're starting to eat into the question and answer period. One can then do that exercise as a function of a number of different temperatures and basically plot this length scale, this wave coalescence dimension, as a function of the inverse temperature. And one can do that very much in the spirit of what Craig Tarver did a number of years ago, we ourselves did, where these two lines are actually calculations as a function of temperature of minimum hotspot diameters in shock physics. Another attempt at getting to a length scale qualitatively as a function of temperature. These are length scales of the dimension of a hotspot that would be necessary to run away thermally or quench. So there's sort of a go, no-go boundary in a shock physics sense. These are dimensions representing the distance over which one would expect coalescence to occur from ignitions calculated at each of these temperatures. And you remember that that we got two derivative spikes in such a calculation, and they manifest themselves as two length scales. And so one can see that even at a single temperature, you've basically got two different length scales in operation when that ignition is coupled to shock physics. We see things like millimeters in a low temperature, sort of safety regime of application of HMX. We have wave coalescence distances on the order of tens of millimeters or meters, which are reflective of work done by Gary Parker et al. At Los Alamos in high strong confinement DDT, or a sort of canonical series of papers, French work from back in the late 90s on long tube steel DDT. If you go to higher temperature, one begins to see dimensions that look more like reaction zone dimensions when you take that reaction zone time and couple it to a detonation velocity. So again, we're beginning to get at the characteristics of these molecules, and we're getting at them in a fairly constrained and fundamental way through these classical kinetic mechanisms. One can do this exercise that we just did with HMX. You can do it with PETN. You can do it with THUB. And this is actually quite wonderful, because now we've got PETN at dimensions of a millimeter or smaller over all temperatures. PETN is something almost like a primary explosive. It is a molecule that appears most often in detonators, and here it is looking like the most sensitive, smallest dimension shock physics molecule we could pick out of this bag of secondary explosives. HMX is more complicated, somewhere in the middle, with a very distinct difference between the sort of molar pressurization that you see in that first spike and this thermal pressurization in the second spike. One interpretation of this is that HMX is a molecule that burns really well. These two chemistries separate. The one can serve as the boundary condition on the other, and deflagration is a feature of HMX, so that it can be a detonator, but it's better as a main charge explosive and probably best as a propellant. And then THEB, which you've got to get way over here in temperature if you want it to even behave like an explosive at all, and we all know that THEB of all of our molecules is probably closest to a piece of wood. At this point, I've really kind of said most of what I want to say. We're starting off trying to understand, through the classical kinetic prism, these molecules. And at the end of all of this, they are beginning to show us who they are themselves when viewed through this prism, with no fitting for any particular behavior, just a natural consequence of putting together these ideas from the crystal lattice, the ignition line, and some intermediate chemistry, and pretty soon you've got a functioning secondary model here that's already qualitatively reproducing a lot of stuff that you know is going to be correct when you go to all the effort of putting it into a hydrocode. I wanted to illustrate a little bit more of this kind of application by talking a bit more about the kind of experiments that Laura does. Essentially, I'll do that quickly so that we still have 5 minutes for questions. You take a detonator, and this is a radiograph of one. You diagnose the crap out of it so that you can generate wave diagrams, measures of the temperature near the volume where we know ignition to occur, measurements of velocities of things emanating from that volume, and coalescence and detonation that we observe as the thing functions. If we take that temperature boundary condition and we integrate, say, our PETN model for it, and we go through this exercise of the method of characteristics, and we get some understanding of the dimension over which we expect coalescence to happen, and then we go back to the wave diagram that we measured during function, the whole thing makes sense. Ignition follows from the boundary condition. It follows from a volume that we observe, which is sufficient to drive coalescence over the coalescence length that we calculate. All of this happens and informs us about the structure of the internal workings of the detonator, and then we observe it functioning at the surface and internally with Lars radiography. And we've published a couple of papers on this, but the whole story is hanging together really well. And it is basically the end of my story. And at this point, I'll leave this up. It's the outline, but now summarized. It is a chance, I hope, for you to understand where we're at with this process. There's still work to be done, particularly understanding the details of those first few steps. Work to be done getting them in complex simulation to validate all of these qualitative ideas with more quantitative simulation. But this, I think, has been a pretty good snapshot of where we're at right now. And thank you to the panel for the opportunity to speak, and thank everyone out there for your attention. And I'll take what questions we have time for. Thank you.
Thanks, Brian. So we have a few minutes for questions. Those who are attendees can see the question, should be able to see the question and answer panel. So please type in a question there, and I'll read it out to Brian so he can address it. We have one. I assume that's from K.O. Springer. How does pressure dependence of melting affect your melt acceleration analysis, as well as the asymptotic rate behavior observed?
That's a great question, K.O. I don't think that the quick answer is that there have not been measurements yet at elevated pressures to base any of this on. So we don't have any melt acceleration information, but that's a fantastic idea for an experiment to create, because that asymptote, again, would still serve, I think, to separate reactivity from melting and allow you to interrogate the pressure dependence of melting in a way that we perhaps have not been able to before. We do have an idea of how well that might work. People have done ignition experiments, not melt acceleration, but ignition in diamond anvil cell. I think that's Ed Lee, Livermore work, KO, where in a diamond anvil cell they cooked off PETN and HMX. And we can see ignition behavior that we recognize using these ideas, and we can get volumes of activation from that. So the short answer is that in ignition, the measurements that have been made seem to indicate that these ideas are applicable. But we still want for experiments which can and allow the melt acceleration phenomena to express itself as a function of higher pressure. Thanks, Gail.
Okay, Brian, we have another question. How much work needs to be done to get this into hydrocodes or other tools for simulation? People
have been doing it with different, The short answer is it depends on the application. I think a number of people, for instance, Uday Kumar's group at Iowa have put in our full dozen step mechanism for HMX into Scimitar 3D, which is a fairly sophisticated, a very sophisticated hydrocode. That took a considerable amount of effort. One can simplify these models. This is an important point. Thank you. We're putting together full models to try to capture the pressurization with the best fidelity. But we can also, now that we have an idea of what that best fidelity is, examine the use of just a single term model and see how that compares. And perhaps one could introduce a single term model into a hydrocode simulation. The introduction of a single term model into a hydrocode might not, likely won't, entail a significant change in the simulation itself at all. I mean, most of them carry along single term models for these molecules. This would just be a different one of a particular functional form. And we would have some better, I think, understanding of how to compare that functional form to the full-up complex model. So the answer is quite a bit of effort to get a full multi-step mechanism into a hydrocode. But a single-term example could be evaluated, for which I don't think the implementation would be that onerous. Thank you.
Any other questions from the audience for Brian? Time for maybe one more. Okay, well, I guess I will take this opportunity then to thank Brian for his very interesting talk, and all our audience for tuning in. Our next seminar again is in June, excuse me, with Neil Bourne. I hope you all will join us for that. Thanks very much, and enjoy the rest of your day.
Thank you very much.